Hello and welcome to my second English video. This is also my 42nd video, and that's why I wanted to do something a little bigger than usual. I wanted to address some of the issues concerning life, the universe and everything, since it's the 42nd video. And I decided to do something about flat Earth. You know, I'm a geography teacher, and seeing these videos on YouTube that the Earth isn't a spinning ball but is actually flat, it makes me very sad. And I would like to address some of the questions flat earthers have. I have some questions of my own, and I know that there are very good videos which have already debunked the flat Earth. One of my favorite channels in this realm is the channel of Simon Dan. I have a link in the description to his channel. It's very funny and educating, and I can recommend this channel very much. As a matter of fact, I think I could never make a video half as good as his videos, and he addressed all of the issues I'm going to talk about. But as I'm a teacher, I know that sometimes saying something in a slightly different way might add some aspects which could help you to understand things a little bit better. And some of these small aspects are hopefully new to you. So I am going to take coals to Newcastle by doing this video, and I hope that I'm able to add some of those new tiny aspects to the following questions. This is my first question. Why can't we feel the spinning of the Earth or the Earth's orbit around the Sun? Shouldn't we feel this speed? You know that at the equator the Earth is turning around with 1,600 kilometers per hour. I apologize here. As I'm German, I will not use the English system, but the metric system with kilometers. I hope you forgive me. Now, shouldn't we feel this speed? As a matter of fact, no, we shouldn't. We don't have a sense to feel or to experience speed. All we can feel is the increase in speed or the decrease in speed, not speed itself. You can all check this for yourself. If you are in a train, you are in the station, you are already late, and the train is there, standing, you are looking out of the window. Finally, we are rolling. We are getting faster and faster, and it was about time. But wait, what's the station doing out there? Oh, it wasn't our train who was moving, it was the train next to us. But since the increase in speed was so slow that we could only see it with our eyes, the moving train next to us fooled us into believing that we were moving. So we don't have a sense for speed. All we can do is feel the speed in relation to another speed. Now, in relation to what are we going to feel the speed of the Earth at the equator? Everything around us, if we are on the equator, is moving in the same speed, in the same direction as we are. Cars, trees, the air, birds, everything. So there's literally no possibility for us to feel this speed. But what about the orbit, the Earth's orbit around the Sun? Shouldn't we feel this? That's fast. Over 100,000 kilometers per hour. But is this really fast? Just look at the size of the Earth. The Earth is about 12,700 kilometers in diameter, and it's moving at a speed of 100,000 kilometers per hour. That means it takes the Earth 7 minutes, over 7 minutes even, to cover the distance of its own size. Now, is this fast? Not really. Every garden snail is faster than that. So, speed is not going to work as an argument for we should feel it. Next thing, which has to do with the Earth's orbit around the Sun. If we are orbiting the Sun, shouldn't the stars shift position in the sky? Yes, they should. They should very much. And we're going to calculate how much they should shift in position. In order to do that, I will explain to you an astronomical unit which is called parsec. If you are between the Sun on one side and the Earth on the other side, you have got an angle of 180 degrees. Now you step back, and the further you are stepping back, the smaller the angle gets. And now I want you to move so vastly far behind that this distance between the Earth and the Sun is only 1 arcsecond. That's minuscule. And if there were any stars so far away, could we see the shifting of these stars? What's 1 arcsecond? Or better, it's 2 arcseconds, because the Earth goes from one side of the Sun to the other. So we have 1 second here, 1 second here, this is 2 seconds. And the full moon has a diameter of about half a degree. That's 1,800 seconds. Now, can we see the shifting of a star of 1/900th of the full moon? Not really. But are there any stars so far away? If the stars are nearer, we could see the shifting. And there are no stars only so far away. The nearest star is 4.3 light years. The parsec I just explained to you is 3.26 light years. So the stars shift even less than 1/900th of a full moon in a year. We have telescopes which can see and measure this shifting. We have them, but with the naked eye, it's not possible. In order to visualize this great distance, I want you to imagine the Sun as a small glass ball of 1.3 centimeters. Then the Earth is 1/10 of a millimeter in 1.5 meters distance. And the next star, where is the next star? If this small ball is in New York City, the next star is a little bit farther away than Washington DC, 400 kilometers. And we cannot see it because it's Alpha Centauri, which is only visible from the southern hemisphere. And the second next star, it's a star we can see, Sirius, and that would be in Detroit. If our Sun is in New York, the next star we can see is in Detroit. The ball like this, a little bit bigger than the sun. The second question is, why don't we feel the curvature of the Earth while flying to another continent? There are flat earthers who say the Earth must be flat because when I'm in a plane, I don't feel that I'm going like this. I should feel it. I should be able to measure it with the right equipment. But these people have a bit of a problem because they don't know what the word up and down actually means. Up doesn't exist in space, neither does down. Up and down are defined on Earth by the Earth. Up means away from the Earth, down means towards the Earth. So, if I'm in New York City, this is my Earth, my position of the Earth. If I climb in a rocket, fly like this is how I will see the Earth. If I do the same thing in Australia, here's Australia, then this is my Earth. For me, the Earth looks like this, because down is the Earth, up is away from the Earth. So there are not two people on the whole planet who have the exact same sensation of the Earth. If the Australian climbs into a rocket, goes like this, he will see the Earth that way. And if I fly from New York to Australia, any minute my personal Earth will change. Wherever I am, the Earth is beneath me, not next to me, not above me. For me, the Earth is beneath. So, for me, it goes like this. And I have not changed my relative position above the Earth. And this goes for any instrument I'm taking with me. So of course, in a plane, I will not feel the curvature of the Earth. Third question. Why do sun rays appear to converge instead of being parallel? We all know that sun rays are parallel. The sun being much bigger than the Earth, its rays are virtually parallel. But why do they appear to converge? If the sun is setting, it's very nice. There are lots of photographs. But why aren't they parallel? I'm going to show you that. I think you will agree that these floor plates are parallel. Magic! Now I'm getting to my questions to flat earthers. How do you explain the angle of the setting sun and the movement of the stars? Why is it that by measuring the angle of the setting sun, I can exactly say on which latitude I am? I've been to Iceland, I've been to the equator, and I have seen the setting sun. In Iceland, the sun sets at an angle of about 35 degrees, so very smooth. Whereas in the Seychelles, it sets like this. How is this possible on a flat Earth with an orbiting sun like this? I cannot see how this would work, but on my globe, it's easy. As I explained, for everyone, the Earth is exactly beneath him. So, my little friend here is on the North Pole. If he's on the North Pole, then for him it will look like this. His personal view will be like this. How will the stars and the sun move? They will move absolutely flat. And that's how all the stars move over the North Pole. That's about the only place on Earth where you could think that the Earth is actually flat. Because there, this could work on the flat Earth model as well. But now for the equator. So starting here, like this. So every celestial object will make one half circle from east to west. On the pole, everything flat. On the equator, like this. It's easy, very easy. And if the North Star is above the pole, when can I see it? Up until here. I will see it. But down here, it's invisible. And on the southern hemisphere, the North Star is invisible. I cannot explain this with a flat Earth. And next thing, the stars on the southern hemisphere function exactly the same as the stars on the northern hemisphere. If you are in Australia and you look south, you see the stars which lie above Antarctica. And from here you see the same stars as you see from here and from here, because they are all there. On a flat Earth model, you have to have the same constellations all around, but in a way that you can never see them twice. They are all once there, but everywhere at the same time. How does this work? It doesn't. Now, if there are any flat earthers watching this, be my guest to rip me apart for any pronunciation error or for my old-fashioned style with blackboard and chalk. But please answer just this question and the ones I have added in this question as well. So much for my 40-second video about a little bit of the universe. I didn't speak about life, I didn't speak about everything, and I hope that I was able to add some tiny aspects to this question of flat Earth, and I hope we see each other soon. Bye bye.